Question number 5. So this is physical chemistry. Question number 6 also physical chemistry. Question number 7 is organic again. Then 8, 9, and 10, inorganic, industrial, and a little bit of redox chemistry. So state Raoult's law. So this should be very straightforward at this point. So you can mention this in your words, or either you can explain using a small diagram. So you can show a small closed system, and you can show the equilibrium between the liquid and gas phase when there is a compound that is equilibrated in the solid and gas phase, or liquid and gas phase. For an example, let's say A and a gas here on the top. And then you can tell the vapor pressure in the gas phase is equal to the mole fraction of A in the liquid phase times the saturated vapor pressure. Or either you can just write down this equation. PA is equal to P naught A and XA in the liquid medium. Okay. And you have to define the terms. That is important. State Raoult's law, you can just write down this equation and define the term. That is totally fine. Or either you can explain it by your words. That depends. That you can choose whatever you use. Okay. But I personally prefer you write down the equation, then you quickly define the terms, and you say this is the Raoult's law in equilibrium system. That's it. Otherwise, you need to draw the diagram and explain it in word. It takes more time actually. Okay. Right. So we are going to do the same type of Raoult's law calculation. So I have mentioned you before. Everywhere, anywhere you go, always in Raoult's law questions, you have to use just two equations: Raoult's law equation and Dalton's law equation. Raoult's law equation for the liquid system using the mole fraction of liquid, and Dalton's law for the gas phase. That's it. So A and B form an ideal solution, so which is very good. So equilibrium with vapor, that is good. So we have A and B. So this is the information that they have given. So A and B in the liquid phase are Na and Nb. So we have Na here, and we have Nb here. So which is good. The saturated vapor pressure of A and B at the temperature P naught A and Pb. So there is no point here. Okay. So we will stop sharing and we will use the board very quickly. It will be easy for us to go very fast and do the calculation straight. Right, so we have the equilibrium A and B. So this is Na and Nb in the liquid phase. So primarily we have given Na is 0.1 mole and Nb is 0.2 mole, and P naught A is given as 10 to the power 4 Pascal, and Pb is given, P naught B is given 3.5 10 to the power 4 Pascal. This is 1 into 10 to the power 4 Pascal. Okay. And calculate the partial pressure of A given that. So this becomes very straightforward because you have given the saturated vapor pressures. Right. So you have given, so you need to just put Raoult's law. So PA is equal to P naught A NA in liquid. So P naught A is given 10 to the power 4 and Na is given 0.1. Is it? Is that the thing that we are going to use? Na. Na means the number of moles, but we are going to go with the XA liquid. This is the mole fraction. So which means 0.1A XA liquid times the total number of mole, which is 0.3. So this is PA. In the same way, you can calculate PB, which is P naught B XB in the liquid. So P naught B is given 3.5 10 to the power 4 Pascal times XB, which is now 0.2 over 0.2. Okay. So using this one and this one, you can calculate the pressures, partial pressures, and you need to calculate PT, total pressure, in the next step. So you just need to add PA plus PB. Okay. So this is a straightforward calculation. So you need to calculate partial pressure of A, just the partial pressure of A. But what you have to understand here, wait. Here you have to calculate the partial pressure of A, but the thing is, in the second part, they have mentioned to find the total pressure. So which gives you the idea, you need to know the partial pressure of B as well. So that's it. Okay. So this is a straightforward Raoult's law question. Gas C dissociated into gases D and E. So you have given this equilibrium. 1 mole of C was introduced into the rigid container and allowed to reach equilibrium at temperature T. It was observed that 0.2 mole of C has dissociated at equilibrium, and the pressure in the container was 1 into 10 to the power, I guess it's 3. Yeah, 1 into 10 to the power 3. Let's see. Some questions are not clear because of the paper is a little bit noisy. Where was that question? Where is it? 10 to the power 5. So that's nice. This is 10 to the power 5. Okay, so you have an equilibrium. So I will stop sharing. Right, so we have the equilibrium. C gas giving 2D gas plus E gas, right? So this is the normal typical equilibrium that they have given. And you keep 1 mole of this, and at the end of the day, it has been found that only 0.2 moles of C has dissociated. So basically, the dissociated amount is 0.2 mole, which means the amount formed is twice of it. So it should be 0.4 moles. And stoichiometry is 1:1. So this should be 0.2 moles that is formed. So at the end of the day, there is 0.8 moles of C that is remained at equilibrium. Okay. And they have found the total pressure, the PT of the system, is 10 to the power 5 Pascal. So calculate equilibrium constant in terms of partial pressures. So you need to find Kp here first. Second one, calculate equilibrium constant, concentration. So this is very easy. So Kc. They have given the temperature as 500 Kelvin. Okay. And when the temperature of the system was lowered to 300 Kelvin, it was observed that these are okay. So there is a separate part. So first we will finish this one quickly. So basically you need to find Kp. So you have the total pressure and you have the number of moles. You can find the mole fraction and apply the Dalton's law. So because Dalton's law says P C gas is equal to X C gas PT. So you need to find XC. So XC here is 0.8 moles over total moles. So total moles you have 1.4 moles. And PC should be equal to XC 0.8 over 1.4 times 10 to the power 5. Okay. So in the same way, you can find the partial pressure of D as well as partial pressure of E. So XD is 0.4 over 1.4. PD is 0.4 over 1.4 times 10 to the power 5. And in the same way, PE is equal to 0.2 over 1.4 10 to the power 5. All these are in pascals, right? Then you need to find Kp. So Kp is equal to partial pressure of D gas to the power of 2, partial pressure of E gas, and partial pressure of C gas. So primarily you know all these and you can find Kp. That is straightforward. Okay. And then if you know Kp, so you know your equation, right? So Kp equal KCRT delta N. If you remember this equation, Kp is equal to KCRT delta N. So you can find Kc is equal to Kp over RT delta N. So what is delta N? It is important to understand what is delta N. Delta N means the difference between the number of moles in the product side minus reactant. So product there is 3 and reactant there is only 1 species. So 3 minus 1 here, your delta N will be 2. And since you know Kp, you know R, and you know T because temperature is given as 500 Kelvin here, you can plug delta N as 2 and you can find Kc here. This is very straightforward, right? These are just theoretical calculation that we commonly do a lot of. Always we do this calculation when you learn theory, okay? Right, so the tricky part comes next. Okay, so always there is a tricky part in the last question. So this is one of the tricky parts that I have come across recently. So this is very nice. So now see what is going to happen. So initially we had temperature around 500 Kelvin and we have C gas that is equilibrated into D gas plus E gas. Okay, so the source temperature was 500 Kelvin. Now this says when the temperature of the system was lowered, so now the temperature is lowered, let's say it has given as 300 Kelvin. In fact, it is given 300. It was observed that D is partially liquefied. Think about this. D is partially liquefied and it is in equilibrium with its vapor. So this same equilibrium lies, but here there is another equilibrium that is going on. The saturated vapor pressure of D at 300 Kelvin is also given. So this vapor pressure, the pressure of this D is given as 5 into 10 to the power 2 Pascal. Okay. The amount of C at dissociated, so now they have given the dissociated amount that is 0.1 mole. So initially we had like 1 mole, here also 1 mole. Then there was like 0.1, this was 0.2, this was 0.4 and this was 0.2. Now at different condition, different temperature. Now they have told us to calculate Kp dash. So find Kp for this particular equilibrium, Kp dash. So we have found already Kp here. There is no problem. Now, how can you find this? This is very important to understand, right? So first we will go through this. So at the equilibrium, they have found that 0.1 mole of C is dissociated, which gives you the idea there should be 0.2 moles here equilibrated. D, because stoichiometry is 1:2. And at the same time, there should be 0.1 of E is formed. Okay. But the problem here is we don't know how much moles that is existing as in the vapor and that is existing as in the liquid state. We know only the total number, which is 0.2. So from this 0.2, it can be like some X value that is in the gas phase, and then the liquid phase will be 0.2 minus X. But the problem is we don't know what is X. That's the problem. Because although if this system is in the gas phase, if this is 0.1 that is dissociated, there should be 0.2, this should be 0.1. But the problem here is from 0.2 here, some amount is liquefied and is now in equilibrium. But we need to find Kp dash. So whatever that we do, we just need to know what is the partial pressure of D gas in order to plug that in the Kp dash equation, basically Kp equation. So you don't need to know this value of X because they have given the saturated vapor pressure of D is 5 into 10 to the power 2. 5 into 10 to the power 2, which you should understand. This is saturated and equilibrium in this situation. So the partial pressure of D gas at this situation is also 5 into 10 to the power 2 because this is the situation that they have given. So basically here you need to first identify P naught D is equal to PD. Okay, because this is a saturated condition, this D is now in equilibrium with its liquid form. And you need to understand at this saturated condition, the saturated vapor pressure should be equal to vapor pressure of the D. Because there is no other compound here, that is liquid and gas. If you have two different compounds, that is liquid and gas, then you need to think about how to find the vapor pressure using the saturated vapor pressure and mole fraction. But here there is only D that is in the vapor and the liquid, which should gives you the idea. The mole fraction is eventually only D, there is no other compound. So saturated vapor pressure should be surely equal to its vapor pressure. Okay. Then there is no problem in applying Kp equation for this D. But the problem arises for this. Why? Because although you know the amount of E that is remaining at the end is 0.1, here at the end it will be 0.9, you need to find the mole fraction in order to find Kp. To find mole fraction, you need to know total number of moles in the gas phase. You know this should be 0.1, you know this should be 0.9, but you don't know the amount of D in the gas phase. Because if you want to find the mole fraction, you need to know total number of moles. Okay? But the advantage here is, in fact, you don't need to know. Why? Because if you consider about the Kp equation, okay, if you consider about the Kp equation, it is Pd gas to the power 2 times E gas over Pc gas. Okay, so Pd gas we already know it was 10 to the power 2. So 10 to the power 2 Pascal times squared times Pe. So Pe, we don't know the total pressure. So Pe, you can use the Dalton's law. So Pe will be 0.1 mole in the second equilibrium. Over total number of moles, we don't know. Let's 0.9 plus 0.1 plus X, which is X. X is the amount of D gas that is in equilibrium. So because we need to know the total number of moles. Okay, so this was C that is remain. So if I write this is the second equilibrium. Okay, and there is D that is liquefied also. Okay, so this will be my mole fraction of E gas times the total pressure Pt over Pc. Again, this is 0.1 The amount of moles that is remaining is 0.9 then. The total number of moles is 0.9 plus 0.1 plus x times the total pressure is again PT, because we don't know the PT as well. Okay. The only thing that we necessarily know is this one, only the partial pressure of D. But to calculate Kp dash, we have no problem. Why? You can see when the expression is written down, you can automatically see these things will be cut. Total number of moles and the total pressure is cut in this equation. So you are only going to remain with 10 to the power 2 squared over, there will be a 0.1 here and 0.9 here. Basically 10 to the power 2 squared over 9. Okay. So using that, you can find Kp. Okay. So this is the simplest and easiest way to identify this particular question. Okay. So did you understand this? Did you understand the concept? Did you understand the concept? That is important to understand. Okay. This is a small trick, because if you are in this particular question and if you try to find the number of moles, total number of moles, and then if you try to find total pressure, you will be ending up with expression, not values. It is difficult to get values. You can get, but you need to solve a lot. Okay. So you need to just have a nice idea here. So although you know the partial pressure of D, so you don't know the partial pressure of C and E. But in fact, if you don't know, you can go like, you know, you don't need to know the total pressure as well as the total number of moles, because when you plug this here in the Kp equation, you can automatically see those two become cancelled. Okay. So it is very easy to identify in that way. Try to identify. Okay. So this is a very nice part. So I have told you in the previous cases also, we don't study this in the typical theory subject, but you can apply here. So you saw one of the applications in the question number 3, where they have combined the ionic equilibrium with the phase equilibrium, homogeneous. And here in question number 5, you can see how they have combined a little part with the chemical equilibrium with the phase equilibrium, heterogeneous phase equilibrium. You see how they have combined? These similar combinations can be even seen in 2018 and 2019 as well, where they have combined chemical kinetics with equilibrium. So this is very nice. Okay. Now to do this one, you should think a little bit. It is not hard, but you should need to think a little bit. Okay. So that is essential.